Welcome back to The Explainer. Today, we're diving straight into the architectural blueprints of organic chemistry, specifically haloalkanes and haloarenes. If you've been working with molecular structures and wondering how we actually build the compounds that literally reshape our world, well, you're in the right place. We're going to break down the structures, the naming rules, the core mechanics, and the actual lab recipes used to synthesize these absolute game changers. Now, to really grasp the weight of what we're talking about, we have to look at their incredible resilience. These halogenated compounds are, frankly, incredibly stubborn. Once they make their way out into the environment, they stick around. Why? Because soil bacteria, nature's built-in recycling system, kind of hit a brick wall trying to break them down. It's a total double-edged sword. That extreme stability makes them phenomenally useful in the lab, but obviously a massive environmental headache out in the wild. And the stakes for mastering these specific blueprints, they're sky high. We're not just playing around with abstract theory here. We're talking about literal medical miracles. Take chloramphenicol, for instance, a chlorine-based antibiotic that's an absolute powerhouse against typhoid, or thyroxine, an iodine-containing hormone our own bodies make, where a deficiency leads directly to goiter. And then you've got the synthetic heavy hitters, chloroquine for malaria and halothane, which completely revolutionized modern surgical anesthetics. These molecules aren't just fascinating, they literally save lives every single day. So, how do we get to those life-saving applications? Here's our roadmap for today's explainer. First, we'll classify the structures. Second, we'll tackle the rules of nomenclature. Third, we're going to dig into the core mechanics of the carbon-halogen bond itself. And finally, we'll wrap up with the methods of preparation. All right, let's jump straight into part 1, classifying the structures and reading the blueprint. So the first thing we do is throw these compounds into different structural buckets, and it all boils down to hybridization, specifically the hybridization of the carbon that our halogen is clinging to. On one hand, we've got the sp3 hybridized attachments. This covers your standard alkyl halides, allylic halides, where the carbon is hanging out right next to a double bond, and benzylic halides, where that sp3 carbon is attached directly to an aromatic ring. On the flip side, we've got the sp2 hybridized attachments. That's when the halogen is locked directly onto a carbon that's part of a double bond, giving us vinylic halides, or directly onto an aromatic ring, which gives us aryl halides. Pinning down this distinction right off the bat is absolutely crucial for predicting how these things are going to react later on. Now, it gets even more interesting when we toss a second halogen into the mix to make dihaloalkanes. Suddenly, location is everything. If both halogens are parked on the exact same carbon atom, we call them geminal halides or gem dihalides. But if they decide to be neighbors and sit on adjacent carbons, they're vicinal halides or Vic dihalides. It seems like a tiny visual difference, right? But trust me, it completely changes their overall chemical identity. Moving right along to part 2, rules of nomenclature. Basically, how we speak the language of organic chemistry. You've probably noticed that a lot of these compounds are still saddled with their old-school common names. Think sec-butyl chloride or neopentyl bromide. And sure, you'll definitely still hear those tossed around in the lab, but the IUPAC system is what gives us a universal, zero-ambiguity way to name them as halo-substituted hydrocarbons. So sec-butyl chloride gets a formal upgrade to 2-chlorobutane, and neopentyl bromide becomes the ultra-precise 1-bromo-2,2-dimethylpropane. The IUPAC name doesn't just label the molecule, it tells you exactly where every single atom is sitting. Which brings us to a really fun puzzle. What exactly do you do when you've got the exact same number of carbons, hydrogens, and halogens, but they're wired together in completely different ways? How do we clearly tell them apart? Well, that is exactly where precise nomenclature flexes its muscles. Let's look at the formula C5H11Br. Believe it or not, there are 8 distinct structural isomers for this one single formula. Without a strict naming system, it would be total chaos trying to communicate about them. But thanks to IUPAC, we can instantly differentiate a straight chain primary like 1-bromopentane from a secondary like 2-bromopentane, or a highly branched beast like 1-bromo-2,2-dimethylpropane. The name itself acts as the definitive structural blueprint. That brings us to section 3, the carbon-halogen bond and its core mechanics. Okay, let's zoom way in on the power dynamic of this specific bond because it literally drives everything. Halogens are significantly more electronegative than carbon. Basically, they're electron hogs. They pull the shared electrons in the covalent bond way over to their side. What you end up with is a highly polarized relationship. The carbon gets stuck with a partial positive charge, while that greedy halogen takes on a partial negative charge. This built-in polarization, it's the engine driving almost all of their chemical reactivity. And we can actually see the physical proof of this dynamic when we look at the bond enthalpies. Just look at this crazy downward trend. A carbon-fluorine bond is super tough, coming in at a massive 452 kilojoules per mole. But as we move down to carbon iodine, it plummets all the way to 234. Why? Well, as you move down the halogen group on the periodic table, the atoms get bigger and bulkier. A bigger atom means a longer carbon-halogen bond, and a longer bond is a weaker, much easier to break bond. It's that simple. Finally, let's get our hands dirty with part 4, methods of preparation. How do we actually build these things? So, a classic starting point for synthesizing alkyl halides is alcohols. They're accessible and easy to work with. You could use hydrogen acids or phosphorus halides to do the job, sure, but that begs a very practical question. Why do working chemists almost always reach for thionyl chloride instead? The answer is just a beautiful piece of chemical elegance. When you react an alcohol with thionyl chloride, your byproducts are sulfur dioxide and hydrogen chloride. Now, what do both of those have in common? They're gases. They literally just bubble up and float right out of your flask. There's no messy extraction or tedious chromatography required. You're just left with a remarkably pure alkyl halide sitting right there in the pot. It's a total game changer. Of course, we can also build these from alkenes. You can add hydrogen halides, and you'll remember that addition follows Markovnikov's rule, a classic concept we all know and love. Or you can just go ahead and add raw halogens. A really cool lab trick here is adding bromine and carbon tetrachloride. When you drip that into an alkene, the intense reddish-brown color of the bromine completely vanishes, giving you a colorless Vic dibromide. It's not just a way to prep the molecule. That dramatic color discharge is literally the go-to visual test for proving you've got a double bond in your sample. And to wrap up the synthesis side, let's talk about halogen exchange. Sometimes you just gotta swap one halogen for another. There are two big name-brand reactions you need to keep straight here. If you want an alkyl iodide, you use the Finkelstein reaction. That's reacting an alkyl chloride or bromide with sodium iodide and dry acetone. But if you want to make an alkyl fluoride, and fluorides are notoriously finicky, you've got to pivot to the Schwarz reaction. That means heating your starting material with heavy metallic fluorides like silver, mercury, or cobalt fluoride. Knowing exactly which recipe to pull from the cookbook is everything. So we've decoded the structural blueprints, translated the names, analyzed the bond mechanics, and walked through the synthesis recipes. But I want to leave you with a real paradox to chew on. We absolutely, fundamentally rely on these synthetic blueprints to create life-saving drugs like chloroquine and halothane. Modern medicine would collapse without them. But those exact same super-stable carbon-halogen bonds that we engineer on purpose, they create molecules that completely refuse to break down in the dirt, leaving a permanent footprint on our environment. So how do we, as the ones actually doing this science, balance our desperate medical needs against our responsibility to the planet? Something to think about the next time you're sketching out a reaction mechanism. Thanks for hanging out with me for this explainer, and keep questioning everything.